My name is Jimi. I'm from Sungkyunkwan University in Korea. Today I'm going to talk about the textile-based wearable sensors using the conductive fibers. Firstly, I will talk about the wearable devices, especially the wearable sensors, and then I will talk about textile-based strain, touch, and pressure sensors, and then I will summarize my talk. As you know, wearable devices are able to be classified into three categories. First one is attachable devices on human skin, such as contact lenses. And second is the accessory type devices, such as watch, clip, earbud, and even jewelries. And the third one is textile-based wearable devices, which are called as smart textiles or electronic textiles. Concerning the e-textiles, the Google presented their project in the last year, the project Jacquard, which is a kind of the touch and gesture sensor using the conductive fibers. So e-textiles are the fabric that have electronic devices are woven inside. So people has craved for realization of smart textile having various functions, such as writing, and display, and controlling some electrical devices, and measuring the body signals. So one of the most widely studied applications for e-textiles is sensory systems. Up to now, wearable sensors were, as shown in these pictures, are very large and bulky, but the future wearable sensors can be textile-based devices, which can be clothing itself. So in order to realize these textile-based wearable sensors, various sensing techniques should be investigated and also functional fibers that have sensing capabilities. And among these textile-based wearable sensors, the strain sensor and touch pressure sensor is the most basic sensors and need to be developed first. And the strain sensor measures the electrical resistance changes when the tensile or compressive strain is applied. And here, the gauge factor is the important factor since it provides the sensitivity information and represents the sensing properties. So in this work, we aim to fabricate the textile-based strain sensor for having high gauge factors. At first, we chose a PEDOT as an electrically conducting and sensing materials, since it is a polymer and the original mechanical properties of the fiber can be maintained. So, as shown in here, the conductive PEDOT layer is directly polymerized on the surface of the polyester fibers, and exhibit the electrical resistance of about 600 ohm at the measured distance of 1 centimeter. And we adapted the sewing machine for fabricating the strain sensors, and generally 2 fibers were needed for sewing. So we used the PEDOT coated fiber for sensing fiber and the bare polyester fiber for interlocking fiber. And as shown in these pictures, the interlocking fibers fix the PEDOT coated fiber and to keep the patterns. To fabricate the strain sensor having the high gauge factors, 2 types of the strain sensor were sewed on the fabric. When the strain is applied on the multi-filament fibers, according to the Home theory, applying the strain on the multi-filaments makes increase the number of the contacting points between the monofilament fibers. So consequently, the electrical resistance is decreased due to the percolation behavior. And when the strain is applied along the zigzag pattern, the force is diverged unlike the linear pattern, which results in less resistance changes compared to the linear pattern. And this graph shows the gauge factor of two types of the strain sensor with the different applied strain. In case of the linear pattern strain sensors, when the strain was applied over 20%, the sensor was unstably operated possibly due to the plastic deformation of polyester fibers. In this strain ranging, the linear pattern strain sensor shows generally the higher gauge factors than compared to the zigzag pattern strain sensors. To demonstrate the possible applications in a body motion sensors, the strain sensor were embedded on the textile as shown in here. Because of the motion of the knee, the bend towards straightened state, the strain is applied to the sensor, which changes the electrical resistance. Therefore, the state of the knee can be identified by resistance values, and it can differentiate the bent and straight state and walking and running actions. And another application is the user interface device. The strain sensor were embedded on each fingers of the glove, and basically it works based on the voltage divider circuit. So when the finger is bent, the sensor resistance is decreased and the output voltage is increased. So as shown in this graph, it is operated well without any crosstalk between each fingers. Using the sensor embedded glove, we could express some of American Sign Languages. To demonstrate the alphabet C, except thumb, all fingers should be halfly bent state, and it can be distinguished compared with the fully bent state and straight state. And to enhance the gauge factor of the conductive fibers, we then tried the combination of the silver nanowire and PEDOT PSS layer. After the silver nanowire is coated, the electrical resistance is decreased over 15 times compared to the case of only PEDOT PSS were used. And it shows the somewhat good sensing characteristics and exhibit the high gauge factors as shown on the right side. And furthermore, we could demonstrate the touch and pressure sensors using the conducting fibers. If the conductive fiber were sewed on the fabric in a specific patterns with the two disconnected lines, it operates as open circuit and keep the high resistance. But conductive surface is touched at this disconnected point, then electrical contact is made and it has the resistance which is able to be measured. And this sensor can detect the pressure differences by the difference of levels of resistance due to the population behavior of multifilament fiber as shown in these images. And when the sensor has the structure that conductive fiber sewed two fabrics are cross-faced each other and fixed using the dual-side adhesive between the conductive fiber at the crossed point, then the capacitor is configured since the dual-side adhesive is electrical dielectrics. So these sensors can clearly differentiate the touched and pressed state. In case of the unloaded state, without any applied pressure, as explained in the previous slide, the capacitor is formed with the conductive fiber as electrode and dual-side adhesive as dielectric. But when fingers is touched at the surface of the sensing point, the another capacitor is formed since the human fingers are electrical conductive and fabrics are dielectric as well. So these two series capacitors make the total capacitance to decrease. In the case of the high pressure is applied at the same point, the area of the capacitor is increased and the thickness of the dielectric is decreased, and it brings that the total capacitor to increase. And I will summarize my talk. We can successfully demonstrate the body motion monitoring sensor and user interface device using the conductive fibers, and we also demonstrate the feasibilities of textile-based touch and pressure sensor using the conductive fibers. And this work is supported by Brain Korea 21 Plus program and National Research Foundation of Korea. Thank you for your attention.